The subject of today's video is hyperbolas, and this is our next conic section. We should have already talked about circles and ellipses, and we're going to draw on some of your ellipse knowledge to change it up a little bit and make it a different shape, a hyperbola. But it's got a lot of similarities to the skills you learned with an ellipse. So first of all, the definition of a hyperbola is all points with a constant difference of distances from two fixed points. If you remember, the definition of an ellipse is all points with the same sum of distance. So like this point, if that's 5 and that's 10, then all the points have to be 15 away. So maybe over here we were 3 and 12, and something like that. But you connect all the points where your sum of distances from the two fixed focal points is the same. Now we do the difference in distances, which with an ellipse, we probably did the string drawing trick where you fix that distance and use it to trace out the ellipse. It doesn't really work with the hyperbola so well. But so it's kind of harder to visualize what a difference of distances would look like, but we'll see in just a minute. So there's your definition. As with our conic sections, all of them, we're going to go from this standard quadratic form, right? This is just a quadratic relation, and we're going to put it into a form that it can be graphed from. You should know this is a hyperbola because the signs of the x squared term and the y squared term, one of them's negative and one of them's positive. So that's what distinguishes this from an ellipse. Remember, if those coefficients of x squared and y squared are exactly the same, that's a circle. If they are both positive or both negative but different numbers, that's an ellipse. And if they're ever opposite signs, then that makes it a hyperbola. All right, so now we need to put it into a form where it can be graphed. And that's going to act kind of similar to what we did with the ellipse. Let's move the 32 over, and at the same time, I'm going to get ready to complete the square. So I'm going to take the 4 out of the x term, and I'm actually factoring out negative 4, which means inside the parentheses I need minus 8x plus the space to complete the square. All right, negative 4, x squared minus 8x. My y clump, I don't have a coefficient to factor out of the y part, or the y squared, so I'm just going to leave it as y squared minus 12y plus room to complete the square, and that's going to equal 32. As with an ellipse, we're going to end up making it equal 1, but we need to start by moving that 32 over to the right. Okay, so now we complete the square. Take half of negative 8, which is negative 4, square that, and you get 16. So I'm going to add 16 right here. Now, I didn't add 16 to both sides of the equation. I subtracted 4 16s from the left. So I need to subtract 4 16s from the right. And 4 times 16 is 40 and 24, 64. So I need to subtract 64 over here to make up for the negative 64 that I did to the left. That's a common mistake, is to not realize that when I add 16 inside the parentheses, I actually subtracted 64 from the left side. Don't forget that. Okay, so now your other one, half of negative 12 is negative 6. Negative 6 squared, 36. So I'm going to add 36 to the right-hand side as well. Now I'm going to write it with completed squares. This on the left should be negative 4 times x minus 4 quantity squared plus quantity y minus 6 squared equals, and let's see, 32 and 36 minus 64 should be 4. All right, so remember with an ellipse and now with the hyperbola, we need 1 on the right. So I'm going to divide all parts of this by 4 to get the 1 on the right. And now I'm going to simplify. Negative 4 over 4 just leaves me with 1. So I have negative And at the same time, I'm going to put my x and y radii inside the parentheses. Some books leave it out, some books leave it in. I'm going to go like this. With a 1, it doesn't really matter. But I have x minus 4 over 1 squared. On the y clump, I'm going to have y minus 6 over 2 squared. The 4 didn't simplify because there was no coefficient on the y part, but I did go ahead and take its square root and put it into the parentheses. Like I said, you might look at a different textbook that says y minus 6 squared over 4 and leaves it that way. That would be just fine. No biggie. I like it this way because if I write it this way, I'm looking at the x and y radii. The x radius is 1, the y radius is 2, and it equals 1, so I know I'm ready. The center is 4, 6, the opposite of the two signs that I see, and now I'm ready to graph. So let's see how graphing this is different than graphing an ellipse was. I need to go to the center 4, 6, make a dot there. And then I'm going to use my x and y radii to not draw like as if it were an ellipse, but I'm going to make a little rectangle. I need to go left 1, left and right 1, up and down 2. So that's going to take me here, 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 and here. Now if this were an ellipse graph, I would just go, there's my ellipse, and be done. But this is a hyperbola, so I want to make a rectangle using those distances. This rectangle goes 1 unit left and right, and it goes 2 units up and down. Now, take the corners of that rectangle and extend, keeping that at a straight line. And I want to make this dotted because these are not parts of the graph. I'm going to distinguish this from an actual part of the graph. A little off track there, but you get the idea. Do your rectangle, extend it corner to corner, and go out beyond the corners. And now I've got a little framework for drawing my hyperbola. So now one of two things is going to happen. Either the hyperbola has points here and here, right in the middle of that rectangle, and it has two parts that open this way, or it has points here and here, and it opens this way. So how do you choose which one? The equation you got when you put it into this form for graphing is going to have one negative clump and one positive clump. I'm calling this the x clump, and it's negative. This is the y clump, and it's positive. And that will always happen because one of your x squared or your y squared was negative to start with. So whichever one of those clumps is positive, that's the direction that your hyperbola opens. So my y clump is positive. Therefore, I'm going to open in the y direction, and y is up and down, whereas x would be left and right. So that's how I decide between the two, open, up, down. So my points are there, and then I just approach my asymptotes. That's what those dashed lines are, asymptotes. And it's not going to be a perfect graph, but it should approach those asymptotes and just be a pretty good sketch of your hyperbola. All right, so every point that on that graph that I just drew, if you took its distance from two focal points and subtracted, you would get the same amount. So where are those focal points? Next question. The focal points are they're found similar in a similar fashion to to the ones we found with the ellipse. With an ellipse, we did basically a squared minus b squared equals c squared. It's kind of like the Pythagorean theorem. We used our two radii. In a hyperbola, it's going to look exactly like the Pythagorean theorem. It's a squared plus b squared equals c squared. All right, and this has nothing to do with right triangles. So when I say Pythagorean theorem, I'm not saying we're dealing with right triangles. I'm just saying it looks just like that. And our A and B are our two radii. So 1 squared plus 2 squared equals c squared. And since 1 squared plus 2 squared is 5, c is the square root of 5. All right, so the square root of 5 is about 2 point something. Let's just call it 2.2, which means that to find my focal points, I need to go on my graph. From the center, I need to go up and down 2.2. All right, the focal points on a hyperbola lie right inside the curves. So I'm going to have one that's about right here, 2.2 below the center, and I'm going to have one that's right here, 2.2 above the center. And so let's find the coordinates. My center, if you remember, was 4, 6. So this bottom focal point is going to be 4. And then I was at a height of 6, but I went down 2.2. So down 2 would be 4, another 0.2, 3.8. All right, focal point 4, 3.8. The top one would be 4, and was it 6, 7, 8.2. All right, so that's kind of similar, but in an ellipse we would have subtracted right here. In a hyperbola we add. All right, if you end up with a focal radius that does not get your focal points inside the curves, then you probably subtracted when you should have added. So you've got a couple things to think about when graphing. Does it open up or down? Does it open left or right? And where are those focal points? All right, so that should wrap up our discussion of hyperbolas. Use what you know about ellipses. Extend it to hyperbolas with a couple minor adjustments, and these should be no problem for you. All right, Young out.